Okay, so given a rational function, if we set the denominator equal to 0, that's going to tell us where the function is undefined, which tells us where it's discontinuous, which tells us then by looking at like everywhere else, right, or the complement of that, where it is defined and finding the domain. So if you set the denominator equal to 0 here, what do you get? -1 and -4. Does the 3 matter? Not really, because 3 is not 0, right? So you've got the product of three things, 3, x plus 1, and x plus 4, the three factors. Zero product property says one of them has to be 0, but it can't be 3 because 3 is 3. The other two, there's an unknown, a variable thing that we can work with. Those can be 0 when x is -1 or when x is -4. So what's the domain then? Everything except toss out -4 and toss out -1. The way you do that, well, the way you write everything as an interval is -infinity to infinity. We want to exclude -4 and -1. If I'm looking at it on a number line, -4 comes up first, right? So if I like crossed part of yours out or circled something and wrote something about the order, it's that you had those switched, right? They should show up in the same order they show up on the number line. So -4 first. And then the way we exclude something is to go right up against it on either side and union where that gap is, where it's missing. So something like that. Okay. Now, vertical asymptotes happen anywhere that the function would look like, number divided by 0. F of, whatever. So if x is -4 or if x is -1, we get 0 in the denominator because the denominator has factors of x plus 1 and x plus 4, right? Those are not zeros of the numerator, though, right? Places where the numerator is 0 would be 5 and -2, and those mean other stuff we'll talk about later. But if I take -4, for example, and plug it in here, I get, well, crud, now I have to do it. 36? I think it's 36. It doesn't really matter. Divided by 0. This is undefined, but what that tells me is that nearby, right, next to -4, I have something that's basically -36 divided by something that's almost 0. When you divide by something that's almost 0, you get back a really big number as an answer, as a result, right? That's why functions do what they do near vertical asymptotes, where they get really steep or sharp or start climbing really fast. It's this kind of thing happening. So that means that this has vertical asymptotes at x equals -4 and x equals -1. If you just wrote the numbers down, I probably did something like circle where it asked for equation and wrote in x equals and took a point off or something. Asymptotes are lines, so we write them as equations of lines because these are vertical. They would be x equals and then wherever it happens. If you had something where you would get 0 over 0, so something where you have a common factor that shows up in the top and the bottom like that, it's still not in the domain, right? -1. There's still a discontinuity there because it's still undefined, but having this factor in the top and bottom, they kind of like balance each other out a little bit. And instead of this asymptotic, really sharp, steep behavior happening, you get just a hole in the graph, like a single point that's not there. We haven't done a ton of that. It's probably shown up once or twice in the homework, and that's about it. That's going to kind of continue to be the case, but again, we need to be aware of it. So I'll just write in here like this has no holes, or removable discontinuities is the fancy name for those. Okay. What What about finding a horizontal asymptote? You look at the leading terms. What are the leading terms here? 2x squared over 3x squared, right? We don't need to multiply the whole thing out unless you want to, but I do need to identify the leading terms, 2x squared over 3x squared. Not just the 2 over 3 part, because I don't know yet if that's the only part that's going to matter. 2x squared over 3x squared. Now, the point of taking the leading terms aside is so that I can think about what happens eventually and look at the kind of overall behavior of the thing. Horizontal asymptotes, really what we're asking about is in behavior, like what happens eventually. If I take these aside, the reason I get to pull the leading terms aside is that in behavior is always about what happens when x is 100 bajillion. So once all the weird stuff in the middle happens, how does this thing kind of settle in eventually? The leading term is always a lot bigger than the other ones eventually. That's why we pull it aside. Now the reason for doing this is that I can do algebra here that I can't do with the whole thing. 2x squared over 3x squared, I can reduce that. X squared divided by x squared is 1. Those cancel, right? And I get 2 over 3. What does that tell us? That y equals 2 over 3 is the horizontal asymptote. So when all of the variable stuff, all the x's reduce out like this, and we just get a number back, that number is the horizontal asymptote. Because what this means is that eventually, when x is 100 bajillion, the top and bottom are basically the same size because of the x squared part, only they're in the ratio of 2 to 3 because of the coefficient part, right? I've got 200 bajillion divided by 300 bajillion. Okay, that's basically 2/3. So that settles in there. When I get just a number, that's where the horizontal asymptote is. If there's an x left over somewhere, like I do that same sort of reducing and it ends up being kind of top heavy. If x is big, then that's going to be big. There's nothing that's going to kind of bring it like to sort of settle it down or make it level off, right? So this would not have a horizontal asymptote then, because it's just going to continue on, up if it's positive, down if it's negative, but it's never going to like settle in. If there's an x kind of left over that ends up in the bottom and it ends up being like bottom heavy like that, then when x is big, this whole thing is just going to get forced further and further down toward the x-axis. So it's going to go to 0. That's where your horizontal asymptote would be. So if you get a number back, that's where the asymptote is. If you have an x left over, I would just say, kind of think about what it does, look at a graph maybe to help you make that decision about whether the asymptote is, either 0, like the whole thing's just flattening down toward the x-axis, or nothing, no horizontal asymptote that it's kind of taking off. Okay, what else? X-intercepts. How do you find x-intercepts? Set the whole thing equal to 0. That's how you always find x-intercepts. That's what x-intercepts are. Now, in practical terms, that means setting the numerator equal to 0. You guys that walked in late, if you want to come find yours. Well, I don't know. 5 and -2. So the x-intercepts, and again, just kind of for emphasis, I'm going to write those as points because they are. The coordinates of the x-intercepts are 5, 0, and -2, 0. So 2 points on the graph where it crosses the x-axis. Okay, and then the last thing I asked you to find is the y-intercept. Again, not special to what we're doing here. How do you always find a y-intercept? Set x equal to 0. Right, to find x-intercepts, we're letting y be 0. To find the y-intercept, we're letting x be 0. And then just plug in 0. So 2, 0 minus 5, 0 plus 2, 0 plus 1, 0 plus 4. 2, 10, 2, negative 20 over 3, 1, 4, 12. So 0, negative 5/3. There's, I can't really, there we go. There's everything. I recorded this, so it'll be in YouTube also, but fire here. Okay. There's everything, right? So again, finding the things is not the hard part. Keeping track of what each thing means and where to look for it is the hard part, right? So this is, conceptually a lot richer, but we don't really need to do a lot of work to get the things once we sort of know where to look. So practice, I'm about to hand you a couple more problems that you can use. I would say, I think the worksheet I'm going to give out, the review thing, has, I think, 2 of them on it. Try one where, you work along with the notes if you need to or whatever, and then like fold the page in half and tomorrow or something, go back and try the other one, just sort of going in blind from memory and see how that goes. Okay. Good. Questions about that? Okay, cool. All right. Also asked you to go home and do this. This is the very end of the 5.3 stuff. How do we always solve inequalities? Set it up like an equation first. Yep, move everything to one side. That part's already done here, right? We're comparing to 0, so that part's already done. If it wasn't, then I'd move stuff around, but solve the equation first. Well, solving that equation is basically going to be the same thing as finding the x-intercepts for this function, similar to what we just did, right? If solving that equation, the first thing I would do is, if you want to think about it as finding the least common denominator, it would be this, multiplied by both sides. On the right, you're multiplying by 0, so it all just goes away. That means that x plus 3 is 0. So x equals -3, right? If x is -3, then the thing on the left-hand side in this original problem is 0, and 0 is equal to 0. So that's one place that this thing can change, right? X plus 3, 2x minus 1. There's x equals 3, right? Okay. This function, though, we're comparing to 0. We're asking where it's great. Is it greater than, less than, whatever it is. 0. 0 is the x-axis. So let's just look at this thing kind of left to right. You tell me, when we're out here, is this function, the blue curve, above or below the x-axis? Above. Okay, then there's this intercept at -3 and it crosses. What about right here? Below. Below. What about out here? Oh, it's above. The only x-intercept, though, was at -3, but there's another place where it changes. What happened from here to here, where we changed our answer from being, sitting below to sitting above again? There's a vertical asymptote in there, right? Okay, so for rational stuff, everything we've done up to this point has been kind of nice and continuous and defined everywhere. We haven't had to worry about how domain affected this kind of question. Here we get kind of an extra layer, right, to things. We also need to think about discontinuities. So we also need to find vertical asymptotes. There are kind of four things that can happen on either side of a vertical asymptote. Either the thing splits like this or like that, or they both go up or they both go down. But whatever happens, and I don't really know that just by looking at it, it's possible that on one side the thing's positive, on the other side it's negative, or vice versa. So we need to check around those. Where does this have a vertical asymptote? At a half. Okay, so there's an x-intercept at -3. There's a vertical asymptote at a half. When I go to solve the inequality, then I'll do it the same way I always do it. Make myself a little number line. But what I'm going to need to mark on there and sort of test around where the intervals are going to get broken up are going to be those points I just found. -3 and 1/2. There's an x-intercept here. There's a vertical asymptote here. On either side or between those points, then, I need to figure out whether the function is positive or negative. For the rational stuff, it's a little harder, well, maybe a lot harder, to just look at this and know for sure what the graph looks like, right? Like last chapter when we did this with quadratics, we could kind of just look at it and know enough, right? Like, oh, it opens up. Okay, so positive, negative, positive, we're good to go, right? I can't really do that here. You can graph it if you want, but I know not everyone's, quite as comfortable with that. So this would probably be a place where I would probably fall back a little on just kind of brute forcing it and saying, okay, well, I'm going to see what happens at -4. I'm going to see what happens at 0, and I'm going to see what happens at 2, and just go positive or negative. See what happens, and that tells me what I need to know. So if x is -4, x plus 3 over 2x minus 1, that would be -4 plus 3 over 2 times -4 minus 1. So -1 over -8, -9. Is that positive or negative? Overall, that's positive. So is the inequality that the question's asking about true or false? True, right? I got a positive thing. Positive is bigger than 0. So when I go to write down my solution set, that's going to be part of it. Same thing at 0, 0 plus 3 over 0 minus 1. Overall, that is negative, which means the inequality is false, right? It's less than 0. The question asked me where it's greater than 0. It's not true there. And at 2, 2 and 3 is 5 over 3, I guess, which is positive, right? And I'm just doing enough arithmetic here to figure out the sign, because that's all I really need, because the question was, where is it bigger than 0, right? Okay, so what's the answer then? -infinity to -3, 1/2 to infinity. What about the endpoints? Think about them one at a time. What happens at -3? If I plug -3 and I get 0, is 0 greater than or equal to 0? Yes. So -3 should be included then a bracket. What happens at a half? At a half, it's undefined. Undefined means I don't know what it is, right? Like literally not defined. So if a thing is undefined, how does it compare to 0? I have no idea. So should I include 1/2? No. It's not in the domain. If it's not in the domain of the function, it can't be part of the answer set for where the function is, bigger than or equal to 0, right? So this solution set that we write down when we solve an inequality, that's always a subset, meaning it's part of the domain, right? This can't possibly be included because 1/2 is not in the domain of the function. So because of vertical asymptotes, because of this discontinuity and domain issue that we have, we get like an extra layer that we need to find the vertical asymptotes and test around those. And also an extra kind of layer to the brackets versus parentheses question, right? This one's included because it's a point where the thing is true. This one's excluded because it's a vertical asymptote that's outside the domain of the function. So it can't be included. Okay, everybody feel all right about that? Or, all right-ish? Okay.